All right, silly people, here's the situation. Um, so we're going to be adding together a couple of different angular momentum operators and operating on the state J1, J1, J2, J2 with the J squared total angular momentum operator. And then Shankar provides this expansion for it. That is J1 squared plus J2 squared plus J1z, J2z plus J1 plus, J2 minus plus J1 minus J2 plus acting on the state. Um, and we're meant to prove that this will provide an eigenvalue that is equal to J equals J1 plus J2, and then use that general form in the next part of the problem. So, um, I mean, we have this expansion, so let's just start operating on the state then. Uh, we're gonna have J1 squared acting on this is gonna make it so that it's H bar squared J1, J1 plus 1, and then we're gonna have J2 squared acting on it, so it's H bar squared J2, J2 plus 1. Um, the J2Z is gonna make it so that it's H bar J2 because M is equal to J2. And then we still have to operate 1Z on it. And that doesn't change the vector. So it's still J1, J1, J2, J2. Um, but then we have raising and lowering operators. So for the first one, we'll still have to operate J1 plus on it afterwards. Um, you're going to have H bar times square root of J2 plus J2 since it's a raising operator. No, this one is actually a lowering operator. So yeah, this is J2 plus J2, and then you're going to have J2 minus J2 plus 1. And it's going to it's going to lower the second M value. So it's going to be J1, J1, J2, J2 minus 1. All right. And then you have the J1 minus and the J2 plus acting on it. So because you have a raising operator acting on J2, M is already equal to J2. It can't go higher than that. So actually the fourth term will go to 0. Actually, I guess that's the fifth term. Wait, 1, 2, 3, 4, 5. Yeah, the fifth term acting on the state will just give 0. So this is what we have so far. Moving right along, continuing to act the JZ stuff on our little eigenvector. We'll have 2h bar squared J1, J2. And yeah, that's it. So it's just J1, J1, J2, J2. Nothing changed there. And now you have a raising operator on the first value of the M. So, I mean, M1 is already equal to J1 again. So, can't go any higher. So, that coefficient is 0. So, we just have this, which is lovely. So, we'll factor out an h bar squared from all that. And then expand those J1, J2 terms. So, it's going to be J1 squared plus J2 squared plus J1 plus J2 plus 2J1, J2, acting on J1, J1, J2, J2, which is going to give you, we can factor the square root of terms, so it's going to be J1 plus J2 squared plus J1 plus J2. acting on J1, J1, J2, J2. So your eigenvalue then is going to, I'm going to factor out a factor of J1 plus J2. So you have J1 plus J2 times J1 plus J2 plus 1. And if you remember, that pretty much takes the form of the total angular momentum squared. So this is J plus 1. So it turns out that our total angular momentum can be taken as J1 plus J2. Awesome. The next part of the problem is to sort of evaluate the right-hand side of an equation that it quotes right before this problem. And that's just saying that you're taking your j squared operator, and we're going to expand it in the same way that we did before, and operate it on the right-hand side of this equation, which reads j1 plus j2 square root times the state j1, j1, j2, j2 minus 1, minus this other radical, this j2 over j1 plus j2, acting on the state j1, j1 minus 1, j2, j2. Okay. So I said that we were going to expand it out again, so that's what we're going to do. So looking at the first term, I'm going to go ahead and factor out a j1 over j1 plus j2. We're going to have j1 squared plus j2 squared plus 2j1z j2z plus j1 plus j2 minus, j1 plus j2 minus, plus j1 minus j2 plus, all acting on the state j1, j1, j2, j2 minus 1. And we're going to subtract the other term, which is going to be j2, j1 plus j2, and then this stuff, so j1 squared plus j2, oh my god, j2 squared plus 2j1z j2z plus j1 plus j2 minus plus j1 minus j2 plus, all acting on the state j1, j1 minus 1, j2, j2. All right. So we're going to have some eigenvalues, obviously. So j1 plus j2, I'm going to open a bracket. And it's going to say, we're going to have an h bar squared j1 times j1 plus 1. We're going to have h bar squared j2 plus 1. We'll have a 2 h bar squared, actually just 2 h bar for now, with the j1z acting on it in the near future. That eigenvalue has to be j2 minus 1, because you have to use the m value. So that's that. And that's all operating on the state j1, j1, j2, j2 minus 1. Okay? But then you also have the raising and lowering operators. Nothing's going to happen to, actually, yeah. something will happen. I'm going to tell you right now that the fourth term, this guy, is going to cancel out because you have a 1 plus here, and it's acting on a J1, J1. J1 is already the maximum value of M1. So when you raise it like that, nothing's going to happen. You're going to get 0. So I'm just going to do this fifth term. So that's going to be J2 plus. So we have H bar J1 minus, and then we're doing the square root of J2 plus J2 minus 1. Nah, it's J2 minus J2 plus 1 times J2 plus J2 minus 1 plus 1. That will be acting on the state. It was a raising operator, so it'll take it to J1, J1, J2, J2. All right. And then with the other guy, closing the bracket, we'll have the J2 over J1 plus J2 term. And then we're going to have some similar stuff. So we have H bar squared J1, J1 plus 1, plus H bar squared J2, J2 plus 1, plus 2 H bar J1Z, and then M2 for the other state was, it was just J2, so this is J2 here. And that is all acting on the state J1, J1 minus 1, J2, J2. And then for the raising and lowering operating bit, you're going to have a J2 plus on the fifth term. J2 is already maximum value of M2, so we don't have to even worry about this part. It's going to go to 0, but we do have to worry about the fourth term for this one. So you're going to have plus H bar times J1 plus acting on this square root. It's a J2 minus, so this is going to be J2 plus J2, and then J2 minus J2 plus 1. Right, and that's acting on. Okay. Continuing, we have this radical term, this J1 over J1 plus J2. Open bracket, we have H bar squared, J1, J1 plus 1, plus H bar squared, J2, J2 plus 1. Okay. Plus 2, now it's H bar squared, J2 times, or actually J2 minus 1 times J1. Okay. All of that working on J1, J1, J2, J2 minus 1. And then you had a term with a lowering operator. So this is going to be now H bar squared. This stuff simplifies to just root 2 J2. And then you have square roots of lowering operators. So we have J1 plus J1, J1 minus J1 plus 1. Acting on J1, J1 minus 1, J2, J2. Okay, and then minus this stuff. So J2 over J1 plus J2, open bracket, we've got h bar squared J1, J1 plus 1 plus h bar squared J2, J2 plus 1 plus 2 h bar squared. And then this is going to be, we had J2, and then we're going to have J2, J1 minus 1. Yeah. And that's all acting on the state J1, J1 minus 1, J2, J2. And we had the raising operator term, so now we're looking at h bar squared. This stuff simplifies to root 2 J2. And then this other guy, it's a raising operator, so now we're doing J1 minus J1 plus 1, and then J1 plus J1 minus 1 plus 1. That's all acting on, it was a lowering operator for J1s. So, no, it's a raising operator for J1. So it's going to be J1, J1, J2, J2 minus 1. Haha. Okay. So we've managed to regroup a lot of the different vectors. So we're going to have to group them together again to get our simplified form. Everything has a factor of h bar squared. Just going to pull that out. And so let's look at the stuff that is multiplied by the J1, J1, J2, J2 minus 1 stuff first. So that is going to be square root of J1 over J1 plus J2. We have this J1 squared plus J1 plus J2 squared plus J2 plus 2 J1 J2 plus, or actually minus 2 J1. And then in addition to that, we have the minus root J2. So it's minus root of J2 over J1 plus J2. This is going to be root 2 J2 times root 2 J1. So it's just going to be 2 times the root of J1 J2. 2 root J1 J2. And all of that is acting on the state J1, J1, J2, J2 minus 1. We have another term which will be acting on the other eigenvector. So yeah, so this time we'll have the roots J1 over J1 plus J2. And then that's simplified to 2 roots J1, J2. And now you have minus root J2 over J1 plus J2, which is multiplied by h bar squared J1, or actually, no h bar squared, just J1 squared plus J1 plus J2 squared plus J2 plus 2 J1 J2 minus 2 J2. All of that acting on the state J1, J1 minus 1, J2, J2. Okay, uh, we're really in the weeds now. Um, we can simplify stuff, obviously. So these guys are funny because you have radicals. So you actually have the root of j2 squared. So you just have j2, and then the radical of j1 will be left behind. And so both of the radicals in this term here are the same. And the same will be said for the other guy. So pulling out the radical, we have j1 over j1 plus j2. And then we still have j1 squared plus j2 squared. But now we're subtracting one of the j2s. Or we're two of the j2s, and we're also subtracting two of the j1s. So this is just going to be minus j1 minus j2 plus 2j1 j2, acting on the vector j1 j1 j2 j2 minus 1. And then that is going to be plus h bar squared. The radicals are the same now, so it's just j2 over j1 plus j2 over here. Where now this guy we had 2j1 plus j2. I'm actually going to flip the signs of everything. So we're going to have this term minus this term. So you'll have j1 squared plus j2 squared minus j1 minus j2 plus 2j1 plus, or 2j1 j2. So it's the same dang old coefficient. j1 minus 1, j2 j2. And if you remember 10 years ago when we started this problem, like these are the same things over here that we started with, these coefficient combinations. So, I mean, going a step further, we can say that this stuff simplifies by a bit more. And also, since this is now like the same form as we started, I'm actually going to just refer to the combination of the radicals and the vectors as the right-hand side, and just saying that j squared right-hand side, and then the funky coefficients will simplify to h bar squared. The silly factors here simplify to j1 plus j2 minus 1 times j1 plus j2. And all of that is acting on the right-hand side now. So we have h bar squared. I mean, that's pretty much, yeah, okay. So we're trying to prove that the total energy, or the total angular momentum J of the system, is equal to J1 plus J2 minus J1. And we pretty much just did that, because remember the eigenvalues for J squared usually just give you J plus 1 h bar squared on the state. So we have the h bar squared, we have the right-hand side. So we have that this is j plus 1 h bar squared acting on the right-hand side if indeed j equals j1 plus j2 minus 1. So that is pretty awesome.